Hello and welcome again to the Theories of Everything program. Viewers, in previous programs we've discussed quantum computing a number of times. We've discussed it from the technical point of view, the social viewpoint and even the philosophical viewpoint. And the race is currently on to develop the first practical quantum computer worldwide. There are a number of teams at beavering away, all using different approaches to the problems involved, and the problems are very significant and very cutting edge, very difficult to solve. But one of the leading centres we have here in Sydney, and that is the Centre for Quantum Computer Technology at the University of New South Wales. And we're extremely fortunate in this program to be able to interview its director, Professor Robert Clarke. Welcome to the show, Bob.
Thank you very much. Nice to be here.
Well, having said all that, how long ago was the centre set up actually here? And sort of what sort of scope is it at this stage?
Yeah.
What sort of...
The centre officially formed around about 2000, well in January 2000.
It's good timing.
But in fact we'd been thinking about setting up the centre for about 18 months before that.
Right,
because of the lead times involved.
Yep.
And had been working on quantum computing for about a year and a half before the centre officially got underway.
Right, yes.
And it was sort of the culmination of a lot of very similar physics and science that we're doing anyway.
Yes, it's in the centre's in the physics within the...
well, the centre really spans two faculties. It's in the Faculty of Science, and there are basically physicists and mathematicians and some surface chemists. Yeah. And then in the Faculty of Engineering we have electrical engineers and computer science people involved in the project as well.
It's a very cross-disciplinary thing, isn't it?
Very much so.
Yeah.
And it's,
but different programs within that, is that right?
So
within that tool?
Yeah, we've basically we've broken up the... there are two main areas that we're concentrating on. Yeah. One is silicon quantum computing, so basically trying to build this on a silicon chip. Yeah. And that is about 75% of our effort.
Yep.
And the other one is optical quantum computing, so trying to do it just with light.
Yes.
And that's about 25% of our effort.
So you're hedging your bets a bit there, are you?
Well, not so much hedging our bets. I mean, I think the two are very complementary to each other in sort of two ways. So the first is that the quantum optics community for a long time have understood these problems and have been talking about it for far longer than the solid state semiconductor community.
Yes.
And so the mathematical and theoretical understanding of quantum optics is very valuable to us because it has analogues in the solid state that we can then make use of. So my colleague, for example, Gerard Milburn, at the University of Queensland, who looks after all of our theory effort, has an international reputation in this area. And basically a lot of that knowledge can be transplanted in.
Yes.
My background is in semiconductors.
Oh, I see, yeah. Well, that makes a lot of sense, doesn't it? Because it's all to do with the quantum theory. It's all based on quantum theory and to do with superposition of states, etc., whether they're photons or electrons.
Yeah, so whether we're entangling the polarisation of photons or the spin of electrons in solids or the charge of electrons in solids. There are many ways to do quantum computing.
Well, this is the key from the viewer's point of view to understand this entanglement of the different states. So you pick a particular characteristic of photons or electrons or whatever. It may be spin, it may be charge, it may be polarisation or electric field or whatever.
Yeah. The key, quantum computing is a difficult thing to explain. In a sort of
in a quick
way. Yes. The thing about it to realise is that classically, in a 0 or 1, you are either 0 or 1, and there's nothing in between.
That's right.
Now, people just have to more or less accept as an act of faith that in the quantum world, you can be, if you have a two-level system such as 0 or 1, you can be all things in between as well, various combinations of 0 plus 1.
Yes.
And therefore, the computer, using all of that extra computational space, can actually take a problem and run all the solutions through in parallel. And therefore it gets this exponential increase in computing power.
And there's sort of, even though there's an infinite number of degrees of freedom between the 1 and the 0, it resolves to a 1 or a 0 each individual quantum.
Well, when you go in and read the state out,
then
it will come down to a 0 or 1, and that's what you're looking for.
Right.
Yeah.
Look, I was stunned, Bob, when I read that I think even a quantum computer with, say, 30 quantum bits, an analogue to an ordinary computer, can do the job of a supercomputer and better. And when you get up to 100 or 200 quantum bits, you're then doing...
Into unknown territory.
Yeah, into unknown territory, yes. And that's probably a little bit distant at this stage.
It is, yes.
Just coming back to the model, the two models, but particularly the so-called Kane model, which I understand you've adopted, the solid-state model, which is embedding phosphorus atoms in a silicon chip, basically. So you're and then linking those atoms together via electrons or electric field readouts. Is that broad? Why did you choose that model in particular?
Yeah, maybe I can just sit back off the question and sort of come back to that. There are many ways that people are trying to implement quantum computing. Basically, you just need a quantum system that has two levels, and you can start to play with that and think, well, can I build a quantum computer element out of this? So the most advanced techniques worldwide initially were atoms in vacuuming trapped by laser cooling. They're very exotic at National Standards Institutes, and David Wineland in the US at their National Standards Institute has actually entangled 4 quantum bits in that particular system. So very
ultra cold,
but difficult to scale. It's very difficult to then go from 4 to many. There are people working with liquids. There are people working with different types of semiconductors. You can work with spin or charge. There are people working with photons. There are people...
Superconductors.
Superconductors is another solid state way of doing it, and that's making some very good progress. So almost every day you read some new idea to do it. Now, so let me come back to the question. So why then are we putting this big national effort into silicon? And why indeed are we also keeping alive the idea of doing optics as well? Now, the answer to that is that there's a general feeling amongst people who are really on the line to build these machines, and there's a big difference between putting forward an idea and actually then assembling a team in a lab and millions of dollars to build this machine. It's our feeling that the best quantum bit, probably the best qubits, are the most difficult ones to build. So single atoms are going to be very good quantum bits. It's
an inverse relationship almost, isn't it?
Superconducting qubits are easy to fabricate because they're just microelectronics technology, basically. They're fairly large, although not that large, electromagnetic objects, and you can build them relatively easily. But our feeling was that although very good progress is being made at the 1, 2, and possibly more quantum bit level, eventually the problem will be the scale up. And we very much wanted to engage in a technology which was genuinely scalable.
That's the key, is it? In other words, it's no good just being able to prove it with 2 bits, unless you can go up to something commercial.
We wanted to make sure that this could go the whole distance. Now, silicon, putting single atoms into silicon certainly is in that category. Putting single atoms into silicon, though, had never been done before. And in fact, when we started the project, Bruce Kane was working here as a research fellow. He came up with the idea of doing this. And at the time when it was published in Nature, most people said, well, that's a very nice idea, but it may be impossible to build, and at best it might be 20 years away. So we thought about this very carefully, mainly because Bruce was here, and we actually came up with 2 ways to build this quantum computer, which we thought we could do on a shorter timescale, and indeed we have. The other important aspect besides the single atom approach is that silicon has $1 trillion industry. And no matter what anybody tells you about quantum computing, a very large-scale quantum computer will probably be the most complex machine that mankind has ever built.
Is that right?
And it's going to require massive national resources. So while government agencies at the moment are probably spending hundreds of millions of dollars on the research. When this shakes down and they're trying to figure out what are the metrics by which we hit the big button and say, right, let's go with that. Now, at the moment, the problem is it's not obvious to anybody what we should go with.
Right.
Silicon is looking very good, but so are several others.
Yes.
And we've got to get to a more stringent stage, which I could tell you about before that button's hit. But when that button is hit,
yes,
there'll be billions of dollars invested to bring this about.
And the fact that the silicon technology is in place, has been for a number of years, to develop semiconductors and so forth, then means a lot in that time. It means that can be
the silicon industry has got the capability,
yes,
the resources, the know-how in silicon,
yes,
to really drive this forward.
Once all the research is completed and the things prove viable, then it can take off.
So part of the finesse of this as a researcher is to realise that at some stage there has to be a tech transfer to industry. And in fact that has to happen relatively early, and our strategy has been an interesting one, and I think one that makes a lot of sense. And essentially our view is that on the road to building a quantum computer, where there are many challenges, you're developing technology which people look at it and say, can we deploy that in the industry right now? One of the key aspects of being a research team to build a quantum computer, as opposed to just investigate it theoretically,
yes,
is that you have to be very practical.
Yes. And
you have to look outside your research lab. We have to interact with government agencies. Governments have to understand the technology. We have to manage the expectation of our funding agencies, so it's not hyped up too much. We have to be realistic about the timescales. We have to set metrics by which we want to judge our progress, and that in itself is an interesting exercise. And finally, we have to interact with industry, because ultimately this machine will be built by industry.
But there is an interplay between governments here as well, the US government and the Australian government.
Yeah, very much so. I mean, most people would be aware that quantum computation has fairly profound implications for data security.
Oh yes, encryption.
Encryption and decryption, and therefore it's of great interest to government agencies, and it should be. We have a very close relationship between Australia and the United States, and in fact we're funded by 4 departments of the Australian government, and also by several agencies in the United States, and we're working very much in partnership with the US. But the nice thing about it from our point of view is that I think, without sort of patting ourselves on the back too much, that some of the sharp-end research is actually taking place in Australia, which is a little unusual.
Which is good, which is
very good for Australia.
It is, and Australians have always been innovative, haven't they?
Very
that's
much
the
so.
strong suit, basically, in our research, and that's happened over. Can I just ask you then, what's the current state of play? Where are you at the moment, and what are any potential major roadblocks left, or is it sort of...
Yeah, the state of play at the moment is, the platform of the centre was, we said, look, we think we know how to build this machine. And there were no known strategies at the time.
Right.
And we've had 2 approaches to positioning single atoms inside the semiconductor host. We call one our bottom-up program, where we do it by using atomic manipulation tools called scanning tunneling microscopes to put the atoms where we want them. It's very
precise, sort of.
It's very precise, and essentially the way we do that, I can almost give you a visualization. You take a flat piece of silicon, basically. You spin on a single monolayer of hydrogen over the top of it, which acts like a mask. You then come along with this tool called a scanning tunneling microscope, which is atomically sharp. You pull off one hydrogen atom where you want the phosphorus to go. That exposes a dangling bond on the silicon that's waiting to grab your atom. You then bathe all of this with phosphorus-bearing gas called phosphine. It literally pulls the atom out of that and pulls that atom to where you want it to be. And you can imagine that it's like a piece of sticky tape. You've just stuck the atom of choice sticking above the surface where you want it. Now the key to this then is to then drill it into the silicon, spitting out a silicon atom, and using the hydrogen mask to make sure it doesn't go where you don't want it to go.
To set it in place, basically.
So we need the mask to stay there while we're drilling it in. And in fact, we've achieved that. And this is the first ever achievement of what we call doping the surface of silicon with atomic precision.
And so,
I always wondered how to do that.
yeah. So you come down with the tip of the microscope, and you put on a voltage, and you blast away one of these hydrogen. It is, and in this picture down here, that's an actual single hydrogen atom that's been removed.
That's sort of an enhanced
Scale. So bright means high, and black means low. So if you take a line scan through there, you get that data.
Okay.
You see the individual atoms? So this chamber in here is where you do that surgery. Superconductors, for example, and some of those have already started, which is compatible with industry for a longer-term commercial type of quantum chip.
That's right.
This is another scanning tunnel microscope, but it's a it has some other features on it. But
So what you can see there is on the left-hand side there's a cone coming in. This is a scanning electron microscope, which enables us to loop up there. So the sample sits down there in the stage. There's no sample in there at the moment. The tip comes from above, and then it scans across the sample surface.
See where you're going with your...
This has never been achieved before in the semiconductor industry, and in fact, it appeared on Science Magazine's front page website just a few days ago. It was entitled "Plonk an Atom Down Where You Want It," and this has been a major achievement. And then we've overgrown with silicon to encapsulate it, and then using very small registration markers, we then align all of our electrodes on the surface up to that buried atom, and hence complete the construction. Now, all of that's called bottom-up.
Right.
And that's building it somewhat perfectly.
Yes.
Now, there has been a quicker way to build it, which we call top-down. And what we've done there is taken, again, the flat piece of silicon. We've coated it with another mask, but this is a polymer or plastic layer on the top. And then using an electron beam machine, we've drilled little holes in the plastic that guide the atoms down where we want them to go. But down each guide tube, we only want one atom to go in, and when it goes in, we need to know it's there. So we've used silicon as a self-detector, and we've engineered a complete detector with the precision to detect one atom being fired into it from above. And so what actually happens is when the atom goes down through the hole and hits silicon, which we collect in a detector, and it gives us a little pulse, a click, we can actually put it onto a loudspeaker. And every time we get a click on the loudspeaker, one atom has gone in exactly where we want it.
And then linking those atoms, how's that?
And to link the atoms, we get them close together. So we put them very close together, and we have metal electrodes on the surface that can either transfer an electron between these atoms, or we can exchange this. They have an angular momentum called a spin, and we can couple these spins together using an interaction between the spins.
Right.
Now, the state of play is that was thought to be somewhat science fiction. And recently in the top-down program, we have built originally little clusters of atoms, and using highly sensitive detectors and electric fields, we've moved one electron at a time between these clusters. And finally we went down to two atoms, which is the core of this whole quantum computer. And we have preliminary evidence for moving one electron controllably between two atoms that we have deliberately engineered into silicon.
Almost at that point,
But the key is you need to be able to engineer single atoms into silicon. You need to control interactions between them, and moving an electron between them is one such way of doing it. And once you start to get a hold of that technology, you're on your way. Now, when I say you're on your way, this is where all the caveats come in. What I call managing the expectation. So we've got a fighting chance now of building a couple of quantum bits and coupling them, and we actually believe in the very near future we may be able to do that. But the whole point about any computer, in fact, but particularly quantum computing, is that the materials around them are never going to be perfect. And the biggest sort of enemy of quantum computation or quantum information, which is very fragile, is a thing called decoherence. So the environment, which is not perfect, is trying to spoil what you're doing.
That's right.
Now, you can you can measure what time scale you can survive before that kills you with a particular quantum bit.
Right.
And then you can say, can I do my computation inside that time scale?
Yes.
Now that's fine at the level of a few qubits, but what you really want to do is to say, well, I'd like this quantum bit to stay alive forever. And so what I'd like to do is to do a thing called error correction on this. And in a conventional computer, the way that it's done is, suppose you have a switch and it can be on or off.
Yes.
And if there's an error and it was on, it will suddenly go off.
Right.
How do you know that error has occurred? Well, instead of just having one switch, you make multiple copies of it, let's say 3, you put them all on, and then if there's an error, one goes off, you take a majority vote and you stay with the majority. And so you say, well, let's stay with them on. And that's how you do error correction in a conventional computer.
Right, yeah.
Now, one of the big breakthroughs in quantum computing was a theoretical analysis that basically said you can do error correction in the quantum world.
Yes, that was fairly recent, wasn't it?
Fairly recent.
Yeah,
and this really led to a realisation that we can build a machine.
Yes,
because any machine
was the problem.
is going to require error correction.
Yeah.
So in fact what we have to do is to not just build multiple copies of the quantum bit, but we have to entangle these multiple copies in a quantum way and with several copies of itself. And never looking at the one that we want to keep alive, we look at the other copies and say, are you okay? And if they're not, we correct everything, including the one we don't look at.
Because that would create the decoherence.
Because if we look at it, we read it out,
Yep.
and we don't want to do that. So we're not allowed to know what is happening while it's doing its computation.
So you do it indirectly.
Right. Now, to do that error correction,
Yes.
you have to do it repetitively. You have to entangle 5 quantum bits, and that is a goal that people want to get to by 2007.
Right. I'm glad you put a time frame there.
So if we can build 5 physical quantum bits, entangle them together to keep one of them alive forever with repetitive error correction, then we've achieved a major milestone.
Then you'll know for sure that you can achieve.
That is a very good, sensible criteria to say, okay, we believe that we can now do this.
Yes.
And then it's a question of architectures, engineering, overheads, finances, all the engineering resources. So the role of my research centre is basically to establish that not only can we build a quantum bit in silicon and get it to work and understand its decoherence time and do something within that, but is to actually fight against that decoherence, do error correction at a small scale level and keep this thing alive. And if we achieve that in our research centre, I believe we'll have made a fairly major contribution to the world's effort in quantum computing. And all of these 10 programs, which I haven't had time to talk to you about, each program, bottom up, top down, quantum measurement, theory, error correction, linear optics experiment, linear optics theory, we have a plan of how all of these pieces of the jigsaw puzzle come together.
Yes.
So what I've told you is just really a snapshot of a very large national effort.
That's why we need another session.
Yeah.
But thanks very much again, Bob, for this fascinating glimpse into this quantum world. And we'll certainly look forward again to speaking to you again shortly. Maybe next year.
It's a great pleasure.
Thanks very much indeed.
Thank you.
I'm David Tao, and you've been watching the Theories of Everything program again. I'll look forward to seeing you again next week.